RSA encryption is when you have you want to send a secret message to a guy named Bob, and Bob has something called a public key, which is two numbers. For this example, suppose they are 7 and 143. So the message you want to send, let's just say it's the number 17. I want to send Bob the number 17. But instead of sending the number 17, instead, I take the message, the 17, I raise it. This is known as E, the encryption exponent. I raise it to the 7th power, which is a large number. Then I divide it by 143, and I send the remainder, which is 93. And there are programs for raising numbers to large powers and modding it by some large number. But 93 becomes the message that gets sent. Now, only Bob knows what's called Bob's secret key. Bob's secret key is also two numbers. In this case, it's 103 and 143. Notice how the second number is the same. That second number is called N. Generally, this is called N also. So E and N are the public key. D and N are the secret key. If Bob wants to decrypt the message, he takes the encrypted message, raises it to the D power, which in this case is 103, mods it by the same 143, and out comes the number 17. It's been decrypted. Now, if you intercept a secret message, it's possible to figure out what the secret key is from the public key. But it requires first factoring this n value. So let's just say, in this case, n is small. It's 13 times 11. If you know that, we take what's called the phi of n, which is 1 less than 13 times 1 less than 11. That's the number of numbers less than 143 that are relatively prime to it. And there's a shortcut. If it's a product of two primes, you just take away one from each factor and multiply the answers together. Now we would just have to solve the equation ED is 1 mod 120, which came from here. Well, E was 7, so 7 times what is equal to 1 mod 120. And there are programs, computer programs, it's called finding the modular inverse of 7, mod 120, because it's something times 7 that gives us 1. And even by trial and error, I'll just demonstrate that D equals 103 does work, because 7 times 103 is 200. 7 times 103, is 721. And 721 divided by 120 is 6, remainder 1, which is exactly what we wanted. Now, the reason why we do that is because if you take 17 to the 7th power, it becomes 93. If we raise that to 103rd power, this becomes 17 to the 721. But 721 can be written as 6 times 120 plus 1. And that 6 times 120 could be written as 6 times phi of 143 plus 1. And we have a rule that if you're modding by 143 and you raise anything to something times the phi of 143, which is 120 plus 1, you'll always get back to what you started with. And that's why RSA encryption works. The steps for decrypting something is just factoring this number, which can be pretty hard, subtracting 1 from each factor, multiplying them together to get this, figuring out the solution to this equation, and then that becomes your D value, and then just raising the intercepted message, the encrypted one, to that exponent, and modding by the same n value as before.